Welcome to the Lynn Hall inaugural symposium. I'll just say a few words, and I should of course thank the Lynn family for giving all this money that refurbished this building. Some of you didn't have the good fortune to be in the previous building like I did, so I think it's a big difference, so we're really happy, and also the Amundsen Foundation that helped build this wonderful conference lecture hall. And about the symposium, there has been one change, or 1.5 changes, is that Professor Tao sent me a message saying that unfortunately due to some family matter he won't be able to come Sunday. However, he told me he will still contribute an article to the volume. He said it's already essentially written. So, and so that's too bad.
So we have to do the volume.
And there's no way we can't. That's right, that's for the other speakers. Okay. So I hope that all the speakers will contribute their articles. And so far nobody has said, well, except maybe for one, has said no. And the important change I wanted to say is that because Professor Tao isn't going to be able to speak, Terry isn't speaking on Sunday, we decided after consultation with our executive officer that to change Alexei Poltorodsky's lecture from Saturday, the second lecture in the afternoon, to Tao's slot, which is Sunday at 10 a.m. And that way we'll have 4 lectures instead of 5 on Saturday, 2 in the morning and 2 in the afternoon. And another small change is that in the afternoon, the first lecture by Ellen Eno will start a half an hour later, like 1:30 instead of 1 o'clock, partly because there's during lunch at Avery Hall tomorrow, which is another beautiful building on campus. We're going to have lunch, and also we're going to have a poster session where we have, I think, 15 or 16 posters prepared by our students and postdocs, so even from undergrads. So, so we'll have a little more time, and okay, that's all I wanted to say. And now let me welcome Professor Aschbacher. He's of course special because he's one of the people who hired me when I came here 30 years ago. So he has a special place in my heart. So he'll speak about the finite simple groups and their classification. Thank you, Michael.
Been around here a long time. Was in the old building off and on for almost 50 years, so I have mixed feelings about this new building. Have some nostalgia for the old Sloan laboratory, but it's nice to see a nice new shiny building like this. So I'll have to play off those two thoughts. So as the title suggests, I'm going to talk about the finite simple groups and their classification. Denninger asked speakers to give expository talks, so that's my plan. As a matter of fact, I hope that anybody with a decent undergraduate algebra course can understand most of what I'm going to say. Anyway, I hope so. I'll see what happens. What am I going to say? What are my sort of things am I going to talk about? Well, I'm going to describe the simple groups briefly. Everything will be brief here. I want to give some history of the study of the simple groups. The proof of the classification is long, very complicated, spread out through lots of different papers. It would be nice to improve that, change that situation somewhat, and I'll from time to time say things about efforts that are going in that direction. Another thing, if you want to prove strong theorems about finite groups, you need the classification, but you need something else too. You need suitable information about the simple groups themselves, and I'll touch upon the sort of information that one needs and the state of the art and how much of that information is actually proved now. And I'm going to start out with some motivation, try to convince you that this classification of the finite simple groups is important in finite group theory. So let's see if I can advance the slides. Seen that long enough. So I'm going to start slowly here and remind you what a simple group is. So G is always going to be a group. Usually it'll be simple. And in any event, a group G is simple if it has the only two obvious normal subgroups, G and the identity subgroup consisting just of the identity element, which I'm denoting here by the. And why do we care about such things? Well, we can consider subnormal series of the sort that's indicated up there. So the first term of the series is this identity subgroup consisting just of the identity. The last term of the series is the group G. And then in each stage in the series, the I plus first term in the series, the ith term in the series is normal in the next term in the I plus first series. So that means that whenever you have one of these subnormal series, you get a family of factor groups. The factor groups GI plus 1 my GI, since we can factor out our normal subgroup GI from the group GI plus 1. And if you stop to think about it, if the group G is finite, then there exists maximal such series, where by maximal I mean you can't make the series longer by sticking in an extra term between GI and GI plus 1 somewhere. And if you think some more, you see that the series is maximal precisely when all of the factor groups in this series are simple groups. Necessary and sufficient condition. So these maximal series are called composition series for the group G, and the factors, the family of factors, is called the family of composition factors of the group. So in general, there are lots of composition series for the group, but this theorem, generally known as the Jordan-Holder theorem, says that this family of factors is independent of the choice of the composition series. So in other words, the group is kind of built up from these composition factors, these simple groups. So in that sense, the simple groups, the finite simple groups, are the building blocks of finite group theory. Of course, you have to be a little careful. How do you stick together all these composition factors to make up your group? So that's at least the suggestion that these simple groups should be important. So here we have our Jordan-Holder theorem. Let's go to the Holder program, which I believe is from the 19th century. My history is a little suspect here. And it's two steps in this program. The first step is to determine and find simple groups. And the second step I'll call the extension problem. And that's the problem of seeing how to retrieve the group G from its composition factors. See what, to go on and use the fact that you know these simple groups to say something about finite groups in general. So we've done the first step here. We've determined the finite simple groups, but that was a pretty hard problem. Maybe just barely possible given the state of the art at the time, or even right now. But this extension problem is probably impossible. There's just too much complexity inherent in trying to paste together these composition factors. So maybe I'll make an unscheduled addition here. Let's look at an example that try to convince you that this extension problem can be very difficult. So let's think about P groups. So if we pick some prime P, and a P group for this particular prime P is just a group of order P to the n for some integer n. And if you stop to think about it again, this is almost implicit from whatever group theory you would have had in your first algebra course. You have a group of order P to the n. The group is, a finite group is of order P to the n precisely when all of its composition factors are of order P for this particular prime P, and it has exactly n composition factors. So these P groups, from the point of view of the composition series, if you can solve the extension problem for anything, you ought to be able to solve it for these P groups, because these groups of order P are somehow the nicest of all the simple groups. And if you sort of look at these P groups from a distance, that seems to be true. They're sort of well behaved. You can prove lots of nice things. Probably you prove some of those nice things in your first algebra course. But if you get up and look a little bit more closely at these P groups, then things start to get really complicated. Or just to give an example, I'll refer to a book by Marshall Hall and somebody senior. So Marshall Hall was probably most distinguished Caltech mathematician back in the 60s and 70s. And this guy Senior was a chemist. And together they produced this book. I think Philip Hall had some contribution to it too, which enumerates all the 2 groups up to order 2 to the 6th. So for example, if you have a group of order 2 to 6, it's going to tell you, amongst other things, how many groups of order 2 to the 6 there are. And if I remember correctly, the correct answer is, let's see, 267. So even for the small numbers, group of order 64, there's lots and lots of 2 groups. And then my memory also is that some people at JPL extended this work of Hall and Senior. So maybe they got up to 2 to the 9th or 2 to the 11th, something like that. And then the number of groups of, say, order 2 to the 11th got very, very big. So already you can start to see that it must be a pretty complicated thing to try to go on even to determine how to retrieve a P group from its composition factors. So, if that's the case, then are these simple groups really important? And the answer is yeah, they really are. Maybe it's the wrong question to ask what all finite groups look like. You don't want to look all that closely at all finite groups. You only want to look at the finite groups that are interesting for some reason. And one reason they might be interesting is they arrive in the context of some problem. So the sort of thing that's happened over the last decades since the classification of finite simple groups is that problems come along sometimes in areas of mathematics other than finite group theory that can be changed into a problem about finite groups. And then you want to solve this problem about finite groups. And an approach which has proven to be very useful is to try to reduce this problem about the general finite group down to a problem about, well, maybe not a simple group, but something that's very close to being simple. So here I call it a nearly simple group. And what this notion of nearly simple means depends upon the problem. And to reduce the problem about a general group down to these nearly simple groups, maybe you can't just reduce that problem, but maybe you reduce it to some related problems about nearly simple groups. And to answer those problems and solve your original problem, usually you need some information. Almost always you need some information about simple groups or nearly simple groups. And typically the sort of information you need is knowledge about the irreducible linear representations. That is to say, recognizing your finite group as a group of linear transformations of some finite dimensional vector space over some field, or its maximal subgroups of the subgroups of the group which are big as possible, subject not to being the group itself. So that's the sort of information that one needs to generate to make the classification useful. Now, I don't know if you're familiar with this article, but the physicist Eugene Wigner, a long, long time ago, wrote about the unreasonable effectiveness of mathematics in solving real-world problems. I think we have an analogy here to what Wigner was talking about. It seems, why so frequently, why so often is it possible to reduce a question about general finite groups down to some related question about finite simple groups? It seems to be true. So anyway, hopefully that supplies some motivation for why these finite groups, simple groups are interesting. In any event, what's certainly true is that most of the deep results about finite group theory depend upon the classification theorem, usually by some sort of reduction process like I talked about here. And from what I've said, we also want to know things about the subgroup structure, particularly the maximal subgroups of simple groups or nearly simple groups. We also want to know about the irreducible linear representations. And I'll say things more about that as we go along here. So maybe it's time to state this theorem, this classification theorem, which purports to tell us what the simple groups look like. So here's what it says. It says each simple group, finite simple group, is isomorphic to one of the following, is one of the following: a group of prime order, an alternating group, a group of Lie type, or one of so-called 26 sporadic groups. Of course, this statement sounds very nice, very short, very clean, simple. But if you stop to think about it, it's almost content-free unless I tell you enough about what these families, fair families, groups looks like. So I'll make some attempts in that direction. Next. So let's start out with the easiest simple groups, and groups in prime order. Probably you remember facts about those from your first algebra course. These are the abelian simple groups. So that means that they have only two subgroups, the group itself and the identity subgroup, since any subgroup of the abelian group is normal. And we know that for each prime p, there exists a unique group of order p. One way to think about it is to look at the integers modulo p and look at the additive group. The integers mod p as a group of prime order p. And of course, the subgroup structure of this group of order p is absolutely trivial. It has just two subgroups. In the representation theory, at least the irreducible representation theory is easy. Okay, so those guys came pretty easily. So what about the alternating groups? Well, let's give ourselves a set of finite order n. And then you may remember that the group of all permutations of this set is called the symmetric group of degree n. And the way we want to think about this thing is as the group of automorphisms of this set. So we have this set, it's an object in the category of sets, and the symmetric group is a group of automorphisms of this set X. We've got our symmetric group represented as an automorphism group with this very nice object, this highly homogeneous object. And from this first algebra course, the symmetric group has a normal subgroup of index 2, half the order of the symmetric group. You denote the symmetric group by Sn and the alternating group by A sub n. So it's half as big as the symmetric group. And maybe you remember that this guy A sub n is a simple group as long as n is at least 5. So we want to study here we have family, our alternating groups, a family of simple groups. And we want to study the subgroup structure of the alternating group and the symmetric groups, because essentially always the symmetric group is the group of automorphisms of the alternating group. So it's one of these nearly simple groups. And because this set is so homogeneous, we can, for example, use this representation of the symmetric group and alternating group to study the subgroup structure. For example, one definition of being highly homogeneous in this context is the following. If you have two isomorphic subobjects of this set, in other words, two sets of the same order, then any isomorphism between those two subobjects extends to a automorphism of the set X. That's one nice property that this particular object here has. And that makes it really easy to get a nice description of the subgroup structure of the alternating group or the symmetric group, and then go on to, with much more difficulty, to get a good hold on the maximal subgroups of these two groups. What's a typical maximal subgroup? You look at some nice structure on this set of order n, and you look at the stabilizer of that structure, this subgroup of the group which is acting on this substructure, like a subset or a partition of the set, or product decomposition of the set. So that's a way to get at the subgroup structure, particularly the maximal subgroup structure of these particular class of simple groups and its automorphism group. Now, what about the representation theory, the linear representation theory? Well, you may have had a course as an undergraduate or a graduate student about the classical representation theory of the symmetric group of the complex numbers, describing the irreducibles, for example, in terms of tableau. And now, to apply the classification, it's not sufficient just to know the representation theory of the complex numbers. You need to know it over lots and lots of fields, for example, over finite fields. But the classical theory of the symmetric group of the complex numbers extends, at least to a certain extent, to theory of the representation theory of the alternating group, and with more difficulty to representation over other fields also. Right? So now we come to the groups of Lie type. And here's where most of the complexity involving finite simple groups lives, with these groups of Lie type. So what is a group of Lie type? Well, I'll try to be a little vague here. It's, amongst other things, it's a finite, linear group, a subgroup of the general linear group in some finite dimensional vector space, let's say V over some field F. General linear group being the group of all vertical linear transformations of that vector space, the automorphism group of that vector space. And for example, if we're interested in finite group of Lie type, and then we're looking at the case where this field F is a finite group. And the general linear group itself is not normally a simple group, but it's very close to being a simple group, so we might as well think of it as being a simple group for purposes of this talk. So that's, well, here's one example of a group of Lie type, the general linear group. If we want to find the others, there's various ways to do it. One way is to look at various forms on this vector space, maps from the n-fold direct product of the vector space into the field F that have suitable linearity properties, and then looking at automorphism groups of that family of forms on the vector space. But there's another way, which is also very profitable. That's to think of this group as being the fixed points of an endomorphism of the suitable algebraic group. So this algebraic group, let's say G bar here, is a group of Lie type over the algebraic closure F bar of our field F. And then we think of G as, like I say, the fixed points of some endomorphism of G bar, which amongst other things will be a automorphism of the abstract group G bar. So for example, if we look at our general linear group, we probably best want to think of it not as a group of linear maps here for these purposes, but as a group of matrices. And then we take some Gauss automorphism of F bar over F and use that to define a so-called field automorphism of G bar, which has fixed points, our general linear group, maybe our finite general linear group over F. We do that by applying this field automorphism to a matrix by applying the Gauss automorphism to each entry in the matrix. And that gives us a nice automorphism of the abstract group, and it's an endomorphism of the algebraic group. So we can use algebraic group theory to talk about finite groups. So that point of view is called algebraic Lie theory, more generally studying groups of Lie type and their various Lie algebras and things like that. So the modern version of this algebraic Lie theory probably starts with Chevrolet back in about 1955. He's had some papers where he showed how to construct what are called ordinary Chevrolet groups, which are basically fixed points of field automorphisms on the corresponding algebraic groups. But then there are other groups of Lie type other than these ordinary Chevrolet groups that are obtained from more subtle endomorphisms of the algebraic group. I'll give one example here. You could look at the GU of V, the general unitary group on V. So I don't know if you know what a unitary group is, but it's a group preserving a so-called unitary form on this vector space. And that's obtained by looking at the fixed points of a map which is obtained by multiplying the field automorphism by the transpose inverse map on these matrices. And I just mentioned here that you can also think of these groups of Lie type as automorphism groups of buildings, but most of you probably don't know what a building is, so it's not so helpful, but it's a useful point of view. So we want to talk about how we can approach the maximal subgroups of these groups of Lie type and what we can say about the representation theory of these groups of Lie type. So the approach vis-a-vis the maximal subgroups is basically the same one, or at least in spirit the same as the one I sort of sketched out for the alternating symmetric groups. You think of these groups as automorphism groups of these forms on this vector space V, and that object X, V together with these forms, is another highly homogeneous object, and you can use this representation of G as a group of automorphisms of this object to study its subgroup structure. Now what about the representation theory, particularly the irreducible representation theory? Well, over the complex numbers, there's a deep theory due to Deline and Lustig that tells you what the representations of these groups of Lie-type, finite groups of Lie-type look like over the complex numbers. And then, just by general nonsense almost, if you know the representations, irreducibles over the complex numbers, then you can use that to pretty much say what the irreducible representations look like over any field of characteristic 0 or any field of characteristic P, where P is a prime, which does not divide the group order. So we're left then with the so-called modular representations of these groups, where we're looking at representations of a group over a vector space, over a field of characteristic P, where P divides the group order. So now for these groups of Lie-type, if you start to think about it, they're linear groups, so they come equipped with a characteristic. If they're finite groups of Lie-type, that characteristic is a prime. It's the prime, which is the characteristic of the underlying field defining the group of Lie-type. So the representation theory of this group of Lie-type depends upon whether this prime P that you're looking at is the characteristic of the field or not the characteristic of the field. And if it's the prime P is the characteristic of the field, then the representation theory of the group of Lie-type, finite group of Lie-type, is obtained by restriction from its ambient algebraic group. And that representation theory is in pretty good trouble. So finally, we're left with a case where the characteristic, let's say R of the field that we're interested in doing a representation theory over, is prime, but it's distinct from the characteristic of the field F. And that's a more complicated situation. There's partial results that are known, but it's a work in progress. So there are 4 classes of groups. I talked about 3 of them, 3 infinite classes of groups. Finally, we come to the so-called sporadic groups. Remember, there's supposed to be 26 of these guys. So you can take 2 points of view about these sporadic groups. There's only 26 of them. Maybe they're not so interesting. Just do things for all but a finite number of groups. That's the point of view that some people take. For example, if you go back and look at an article that Michael Attila wrote in Mathematical Intelligencer a long time ago, that's the point of view that he takes. But other people think that maybe these sporadic groups are somehow the most interesting of the simple groups because they're sort of 26 accidents that occur because very special things happen, and those accidents are maybe more interesting than the stuff that goes on in general. So it depends upon what sort of mathematician you are, I think, whether which of these classes of groups you find most interesting. So maybe I'll talk a little bit about the history of these sporadic groups. Historically, it's good to think about the work that was done on them as falling into 3 major categories. One is the discovery of the sporadic group, whatever that means. The next is the existence, proving once you've discovered the group, you have to prove that what you discovered is actually there, that it actually exists. And finally, the uniqueness. You want to prove that this simple group is unique to whatever subject to suitable properties, presumably the properties you use to discover it. So, roughly speaking, one of these sporadic groups, G, was regarded to be discovered when, well, somebody investigates some problem involving some hypothesis and starts to prove things about some group which satisfies this hypothesis. And in the process of trying to study such a group, generates lots and lots of information about the group. For example, typical information that you might want to generate would be the group order, the so-called character table of the group. You know what a character table is, and you know what it is, and otherwise we won't worry about it. In any event, what you want to do is generate a bunch of self-consistent information, which, amongst other things, would include the group order. And once you have enough such information, then the group historically was regarded as being discovered. And then the problem is to go on and show that actually such a thing exists, to prove the existence, and then probably later to prove uniqueness. And if you know some finite group theory, these sporadic groups have names attached to them, and the names are for the most part, names of people, the person who discovered them. Sometimes there's two names attached to them, the person who discovered it and the person who proved its existence. There's one, the largest sporadic group is known as the monster, because it's big. Something like 10 to the 56, I think is the word. So let's talk a little bit about these sporadic groups. So there's 26 of them. The first 5 were discovered back in the mid-19th century by a Frenchman named Mathieu. And there was some controversy about whether these objects actually exist. That controversy went on into the early 20th century, but they did exist. So that leaves 21 modern sporadics, and the first of the modern sporadics was discovered in 1965 or thereabouts by Janko, a Yugoslavian who was working in Australia at the time. And he discovered it by something called local group theory. We'll get around to it in a while. Some of these groups, many of them were discovered via this local group theoretic considerations, others were discovered by other considerations. And after Janko discovered the first of the modern sporadic groups, it turned out that sporadics continue to be discovered at the rate of pretty consistent rate of about 2 a year for about 10 years. And Janko also discovered the last of the sporadics in 1976. So since we're at Caltech, let's look at an example that involves Caltech. So here Marshall Hall comes up again. So Janko discovered the first of the modern sporadic groups, and he also discovered the second and third of the modern sporadic groups. And they're, again, using local group theory. Janko is a local group theorist. And these two groups are denoted by J2 and J3. J for Janko, and 2 and 3 for the second and third Janko group. And the first of these groups, J2, was discovered about roughly the same time that Marshall Hall discovered the same group, and only by a different process. Maybe Hall discovered it a little bit after Janko. So again, Marshall Hall was a professor here back in the 60s and 70s, very distinguished mathematician. He was a senior faculty member at Caltech, so the junior faculty members that worked on finite groups in those days didn't call the second Janko group J2, we called it HJ. H for Hall and J for Janko. So, and many other people did too, also called the Hall-Janko group. And the way that Hall discovered this group was by something called a strongly regular graph. So here's, roughly speaking, what a strongly regular graph is. It's a graph, let's say gamma here, such that the automorphism group of this gamma, the group of permutations of the vertices that permutes the edges in the graph, that this automorphism group is transitive on both edges and non-edges in the graph. Okay? So after Marshall discovered this group from this point of view, many other sporadics, many handful, were discovered by the same sort of process, looking for these strongly regular graphs with a big automorphism. And indeed, quote this one little story about this stuff. Marshall gave a talk about this group in his version of J2, HJ, in Oxford. And sitting in the audience were two group theorists, Higdons and Sims, and they went out afterwards and over dinner constructed, using the same sorts of ideas, constructing a strongly regular graph. They constructed their own sporadic group. So let's see. All right, so I want to devote essentially the rest of this talk classification of the finite simple groups. which we'll abbreviate by CFSG. So I want to give you some very vague idea how you can determine all the finite simple groups, classify them. So normally, when one classifies some class of objects, you associate to each object that you're trying to, in the appropriate class, some set of invariants, and you say that this set of invariants determines the object up to isomorphism. So we want to associate some invariants to our simple groups, or finite simple groups, and the invariants that were used were the so-called local subgroups. So we want to talk about some local group theory. So here's what local group theory means in the context of finite groups. So local depends upon the choice of some prime here, let's say little p, some finite group G. And then we can talk about the so-called p-local subgroups of G. So what is a p-local subgroup of G? Well, we pick some non-trivial p subgroup, capital P of G. So its order is a power of this particular prime p. Its order is greater than 1. And we consider the normalizer in G of P, that's the largest subgroup of G in which P is normal. Such an object exists. If you've had a decent course in algebra, you recognize some of these things from Sealow's theorem, which is sort of the first theorem of local group theory, local finite group theory. So this local finite group theory studies finite groups from the point of view of these local subgroups, the normalizers of non-trivial p subgroups for various primes p. And of course, it's only interesting if p divides the order of the group. So here's an example of a very special sort of local subgroup. Given the subgroup X of G, we can also consider the centralizer in G of X. Denote that by C sub G of X. And that consists of all elements in G which commute with every element of X. Well, that's a little less Sealow's theorem. We're used to looking at normalizers, maybe not centralizers. And in involution, I want to define for you what I mean by an involution. In involution, our group G is an element of G of order 2. So for a group G has an involution precisely when it's a even order. That's Cauchy's theorem that you had in your first group theory course. P divides the order of a finite group, there's an element of order P. So in a group of even order, you're going to have a involution element of order 2. Conversely, if you have an element of order 2, it's 2s to divide the group order. So then, if we pick such an involution, then we can look at its centralizer, and it turns out that if you stop and think about it just a few seconds, that's the two local subgroup of G. It's the normalizer of the subgroup generated by this involution, the subgroup of order 2. So we want to use these involutions to start to say things about simple groups. And the first person to really do that in a systematic way was Richard Brouwer, an important mathematician. He gave a talk in 1954 at the International Congress of Mathematicians. Mathematicians get together every 4 years and have international congresses. This one was held, I forget, Stockholm or something. And what Brouwer proposed in his talk in 1954 was that we should study finite simple groups from the point of view of involution centralizers. And to show that this was an interesting point of view, he and his student Fowler proved the following thing. Suppose you have a finite group H. Then they prove that there's most a finite number of finite simple groups G which possess an involution T whose centralizer is isomorphic to H. So Brouwer is suggesting that involution centralizers should be amongst, he said, the interesting invariants by which we classify groups. We want to classify objects, we want to associate invariants to the object which determine an anti-isomorphism. Brouwer is suggesting here that involution centralizers are a good place to start. Well, there's one problem with this approach. involution if and only if it is even order, because the order of an element divides the order of the group. And conversely, of course, if the group is in even order, then by Cauchy's theorem, it does have an involution. So this approach of Brouwer's is only good if you're looking at groups of even order. Well, around the turn of the century, that was the 19th to the 20th century, not the 20th to the 21st century, a guy named Burnside, an English mathematician, one of the first great finite group theorists, conjectured that each non-abelian finite simple group is of even order. So it should possess an involution, and you can look at the centralizer of these involutions. So that suggested that Brouwer's approach could be workable, viable, and in 1963, Feit and Thompson proved this conjecture of Burnside, and he used something called character theory plus local group theory. So in the initial years of the study of simple groups in the 50s and 60s, character theory, whatever that is, was important, but it sort of faded out of its utility, became less important as we were looking at larger groups. All right, so given this theorem of Feit and Thompson, the so-called odd order theorem, we can adopt Brouwer's approach and focus on involution centralizers. So an involution centralizer is an example of a local subgroup. It's the normalizer of the subgroup of order 2 generated by the involution. So we want to not only look at involution centralizers, but more generally look at local subgroups, the normalizers of P subgroups, particularly the normalizers of 2 subgroups. If we're going to do that, 3 problems sort of obviously make an appearance here. The first problem says, what do involution centralizers, or more generally local subgroups, look like in simple groups? And I suppose along the same lines, how do these local subgroups, how do they differ from the local subgroups in more general finite groups? Okay? And I won't really tell you what the answer is, but that's a problem you have to consider. Second problem, prove that each finite simple group contains an involution centralizer, or perhaps local subgroup, resembling one in a known simple group. Okay? And then the third problem, the involution centralizer problem. Given a potential involution centralizer, or perhaps local subgroup, determine all the simple groups with such an involution centralizer. We're going to concentrate on involution centralizers, and these are going to be amongst the invariants that we're going to use to determine our simple groups. So, interesting invariants that we might want to use are the group order, but another interesting invariant is going to be the centralizer of an involution in the simple group. Now remember, Janko discovered at least 3 sporadic groups, J1, J2, and J3. It turns out he also discovered the last sporadic group, so he's discovered 4 in total. Last one is J4. And Janko was a local group theorist, so all the simple groups were discovered will have involution centralizer problems. All right, so maybe I'll get to some harder stuff now. I'll make some technical definitions here. State theorem. All right, so we've got our finite group G. I'm going to write O sub 2 of G for the largest normal subgroup of G of order of power of 2. 2 subgroup being a subgroup of order of power of 2. Such a thing exists. It's straightforward to see that. So O sub 2 of G denotes the largest normal 2 subgroup of G. Largest normal subgroup is orders of power of 2. And we define G to be the characteristic 2 type if for each 2 local subgroup H of G, 2 local, I didn't tell you what it is, I guess. It's a normalizer of the 2 subgroup of G, non-trivial 2 subgroup of G. So G is a characteristic 2 type of each such 2 local subgroup of G has the property. We look at the centralizer in H of O2 of H, that should be contained in O2 of H. So every element which centralizes, commutes with every element in O2 of H should already be in O2 of H. So for some reason, we're interested in these groups of characteristic 2 type. Now we have these groups of Lie type. Remember, the third family of finite simple groups was the groups of Lie type. And each one of those groups of Lie type came equipped with a finite field. And of course, we all know, don't we, that every finite field has a characteristic which is a prime. And it turns out if we're looking at a group of Lie type over a field of characteristic 2 of even order, then G is of characteristic 2 type. So we can see that this notion is interesting. Here's one of the classes of simple groups that we're going to have to confront. There are these groups of characteristic 2 type. All right, so next let's define our group G to be quasi-simple. So it's going to be close to being simple, but not quite simple. Well, G is its own commutative group, whatever that means. Some of you know what a commutative group is and some don't. So G is quasi-simple if, in the first place, it's its own commutative group. Sometimes that's said, G is said to be perfect, but that satisfies that property. And G modulo center is simple. Center being the subgroup of all elements in G which commute with every element of G. So this is a group. What this means is that group is, G is pretty close to being a simple group. It only differs from a simple group by elements in the center. And finally, the 2 rank of G, which we'll denote by M2 of G, is the maximum integer n such that G is a subgroup that's a direct product of n copies of the group of order 2. And these are all technical definitions, but they turn out to be important, interesting ways to look at finite groups. So here's a theorem. Theorem that includes a whole bunch of sub-theorems that took a long time to prove over a period beginning, well, actually going back to people like Burnside, who was doing his finite group theory in the late 19th century and early 20th century, and then continuing on into the 70s and 80s. So the theorem says, let G be a finite simple group. 2 rank of G is greater than 2, or probably will find the 2 rank of G. It's the biggest integer n such that G has a subgroup which is isomorphic to the direct product of n copies of the group of order 2. And either G is a characteristic 2 type. Here's a definition of characteristic 2 type. This O2 of G contains its own centralizer, its largest normal 2 subgroup of G. Or something very special happens. So there's a lot of things that are going on to this in this second case here. There exists one of these quasi-simple groups, subgroups L of G. Just think of it as simple, if you like, such that a CL2 subgroup, Q of the centralizer in G of L, that's the subgroup consisting of all the elements that commute with every element of L, is non-trivial. So there's some non-trivial 2 subgroup commuting with every element of L. L is normal in the normalizer in G of X for each subgroup X of this group Q. And Q is a very special 2 subgroup. It's either cyclic, quaternion, or 4 group. You may not know what a quaternion group is, but if you have your first algebra course, then you presumably know what a cyclic group is. 4 subgroup is simply the non-cyclic group of order 4, direct product of 2 groups of order 2. So there's a lot of information built in here. If we're going to do local group theory, looking at local subgroups, and here we have a nice local subgroup, the normalizers of the various local subgroups and normalizers of these various subgroups of Q. And these things have a very special form, apparently, according to this theorem. So I'm not going to say much about case 1 here. Don't have time. There's a program, well, it's handled in the original proof of the classification, but there's a program given these 3 German mathematicians to produce a better treatment of these groups of characteristic 2 types, simple groups of characteristic 2 types. In case 2, it remains to solve the corresponding involution centralizer problem for each quasi-simple group L. So, back here, we take an element of order 2 inside this group Q, it's 2 subgroup, And its centralizer is visible in this picture here. And we're going to use those centralizers as our invariants to classify our simple groups in terms of these invariants. But there's at least one problem with this approach here. Let's let L be a known simple group. One on our list of simple groups we're trying to prove is a complete list of simple groups, finite simple groups, and form what's called the Wreath product of L by the group of order 2. And what is this Wreath product? We take the direct product of two copies of L, let's say L1 and L2, and we embed that in a group that's twice as big. And that group that's twice as big possesses some involution T, which when we conjugate them, one of these normal subgroups isomorphic to L, and the subgroup at index 2, we interchange these two subgroups here. So maybe you can picture what that looks like. Well, if we do that, then the centralizer in this Wreath product of this involution is isomorphic to the direct product of the group of order 2 with this subgroup L. And if you stop to think about it, go back and look at case 2 back here. It satisfies all the conditions in case 2. But it's not a simple group. But it's hard to tell just looking at these local subgroups, these two local subgroups, the normalizers of two subgroups, that the thing isn't a simple group. So, I'm dead heat here. I have to perhaps talk for another minute. I think that the proof of the classification theorem should be restructured so as to avoid having to deal with this type of centralizer where a lot of effort is put in and you don't actually arrive at a simple group at the end. And the way that I'm trying to do this is to work in a different category, not the category of groups, but the category of objects known as fusion systems, which I don't have time to explain, but it's kind of partially a group theoretic category, partially a topological category, and it allows one to avoid problems like the ones that arise here. Okay, so my last slide. So there's a classification theorem which says that if you have a finite simple group, then it's on some list of groups. We saw what that list of groups was earlier. But it's a very long, difficult proof. Hundreds of papers, thousands and tens of thousands of pages. One wants to simplify the proof, write it down more carefully in one place. And two people that are doing that are Richard Lyons and Ronald Solomon. And they have a projected 12-volume set of books in which this proof will be written down in a fairly complete form. It says here that they have 7 of those volumes already published, and actually the 8th volume just came out recently. Well, maybe I'll stop there.
Any questions or comments? So what's the role of quasi-thin groups in the classification? Are they kind of very similar to Lie-type groups?
Remember, we divided the simple groups into 2 types. Characteristic 2 type and this other type.
Right.
Because the thin groups arise in family of characteristic 2 type groups. So a quasi-thin group is a group of characteristic 2 type, and it has an additional property that says basically that the local subgroups, 2 local subgroups are narrow.
So are they like groups of Lie-type of small rank or something? Or they, no?
Yes, that's the generic example of such a thing. Sure.
Yeah.
What? Is there a high-level reason for 26 quadratics?
Not that I know.
Can you be a little nervous that there might be a 10
Yes.
working out here?
Yes.
So there's no high-level reason for 26. You only got
There's
down
no-
to 12.
26 is the magic number.
So, Michael, since this is being recorded, could you repeat each question? Maybe, yeah, okay.
He says, is there a good reason why there are only 26 spreading groups? The answer is no. He also asked, maybe there's a 27th spreading group. And the answer is Hopefully no.
We can rename them A to Z.
Can you say a word on your fusion categories? What are they?
Fusion categories.
Is that called fusion categories? It was too fast, I couldn't follow. It's the last before the last slide.
Fusion system.
Fusion systems, sorry.
Fusion systems.
Yeah.
You take a P group for some prime P, and you build a category. The objects in the category are the subgroups of the P group. Let's call it S. And the morphisms from between two subgroups, let's say P and Q of S, are injective group homomorphisms from P and Q.
Okay.
Some fairly weak set of axioms to satisfy. So that's a fusion system.
That's a
And
fusion
amazingly
system.
enough, one can prove lots of things in that setup, just with these relatively weak axioms.
Are there other invariants that you can use to classify the finite simple groups? Besides
A priori. You mean a priori? After the fact, sure. I mean, these local subgroups were chosen because people could make them work.
Okay, any other questions or comments? If not, let's thank the speaker for a great talk.